next speaker is Josef Svoboda for the University of Miami, and he will tell us about the Ż-invariants and universal Abelian covers.
Hello, everybody. In this talk, I'll be talking mainly about three manifolds and a little bit about surface singularities. So let's consider plumbed three manifold M, which is a Q homology sphere. So this is an easy kind of manifold. So this condition that it's a Q homology sphere means that if you look at the H1, the first homology group, then it's a finite Abelian group. So it will be even more special. I will mostly talk about ciphered fiber spaces. So that means that the plumbing graph is actually a star. So I will talk about these manifolds and study some of their invariants. And so maybe why do we care about these manifolds is because they are natural source. So the natural source of them is isolated normal surface singularity. So if you have a isolated singularity in a complex surface, then you intersect with a 5 sphere and you will get a nice three manifold close to the singularity. So if the singularity is quasi-homogeneous, this is exactly when the plumbing graph is a star, or when this three manifold is ciphered. And also we will consider the covering of X. So this is a classical theorem that we can remove a point in the singular point, and we can find a covering, the universal Abelian covering by the H, by this H1, and we can put again a singular point, so we have a ramified covering. And if X is quasi-homogeneous, then this covering is a much simpler kind of singularity. It's actually just this Brieskorn complete intersection type, which means that the equations are given by in the diagonal form x to some power plus y to some power, etc. Yeah, so I want to think about the relation of this manifold and this Abelian covering. So the basic schema is like here. So we have a singularity, we can consider its link, by which we forget a lot of information because there are many singularities with the same link. But we can get, so for many singularities, or like for kind of simple singularities, we can get the universal Abelian cover of this singularity in terms of combinatorics of this three manifold of this plumbing graph. So this is so-called splicing graph construction, and using the plumbing graph, we can also reconstruct the action of H. So here, what I mean by this construction, it's actually just a family of singularities rather than a specific singularity, because you cannot get the analytic structure. Of course, you cannot get the analytic structure out of the three manifold, but you can still get some equations with some arbitrary coefficients, and this tells you something about the three manifold. So here are some examples. So this talk is mainly just examples. For example, we take the famous equation x squared plus y cubed plus z to the 5. This is so-called E8 singularity, and the reason why it's called like this is because if you look at the link, this is the famous Poincaré sphere, and here, and the plumbing graph of this Poincaré sphere. So basically the graph which you use to get this manifold out of S3 using surgery is just the usual E8 linking diagram. Then the next example which I want to consider here is S12. It's one of the 14 Arnold unimodular singularities. And this singularity has also kind of nice link with the ciphered invariants 3, 4, 5. I hope, I hope it's clear this notation. So these are the denominators, the multiplicities of the fibers. and this is just this number in the middle. So we could also use the reduced invariance if we subtract this -1 and we add it here. Yeah, so we get this star-shaped graph, and this is maybe a more interesting example. So it's the equation looks very easy, but if we do the link, because of this, the fact that these two numbers are not coprime, we will get actually 4 singular fibers, which means that the graph is the star with 4 legs. So for these examples, I want to consider some nice invariants. So let's start with some notation. So I will talk about these Z hat invariants. So they are usually written in terms of some Q. So there are some Q series. So they can be sometimes written in terms of false theta functions. So just the notation. So if we consider Q, which is e to the 2 pi I tau, and Y, actually I don't need this, sorry for that. So just we have a variable Q, which is, and we consider natural number M, which we call modulus, and the residue class modulo 2M, which is R. So then false theta function, or sometimes it's also called Eichler integral of modulus M, and the residue class is R, is this function. So we take an infinite sum of this quadratic terms, so Q to the quadratic expression in terms of N, and we sum over the residue class, and also we add this funny sign, so that's why it's called false theta function, because it's not really a usual theta function. It doesn't have this nice modular form property, but it has some weaker modular property, sometimes called like quantum modularity of Zagier. So these functions are important for us, and we can also write them in a different way. This is just rewriting it. So we can write this as a sum of over positive integers. Now we have this character here, so it's basically the same thing. So it's 1 if N is congruent to R modulo 2M, and it's -1 if it's congruent to minus R. Yeah, so these false theta functions, they occur naturally when we consider these invariants of 3 manifolds, and they are also interesting for number theory because they have these modular properties. So this is a link between 3 manifolds and number theory, which was explored by many people. There is this paper of Lawrence and Zagier, which first considered this Q series. When we write it in terms of this character, we can actually just forget about these quadratic terms, which are interesting for number theory, and we can just repackage this character in terms of a generating function. So instead of taking Q to the N squared, we just take X to the N. And if you compute this, it's very easy. You get X to the M minus R minus X to the negative M minus R over X to the M minus X to the minus M. So very simple expression. And basically, if you want to study these functions, you can also just take a look on these generating functions or these characters. Yeah. So now we have the notation. So the false theta functions psi and the corresponding generating functions f. Yeah, and here is the main definition. So you probably saw it many times because this is now very popular among many people. So there are these Z-invariants defined in the paper of Gukov, Putrov-Pei, and Waffa. So given a plumbed manifold, so this special kind of manifold, we can use the plumbing graph to construct a Q series invariant. So if we call M the plumbing matrix of the manifold M, sorry for that. So I had this formula, so I just call M now here. It means the matrix. So we take the graph and we take the matrix. So on the diagonal there are these numbers 3, 1, -1, and there is 1 if they are connected by an edge. So this is like 4 times 4 matrix. This would be like 5, 6, 7, 8, 8 times 8 matrix. So it gets very big when you consider like higher numbers over here. So we consider this big matrix, and we take the theta function of this matrix. So it's an infinite sum of this quadratic term. But now the quadratic term has more variables. Yeah, has as many variables as are the vertices of the graph. And then we add some integrals in some dummy variables ZV, which are assigned to each of vertex, and we add these terms, and finally we integrate over the unit circles so that we basically get rid of all these variables ZV, and we get some nice Q series expressed just in terms of Q. So these we basically just take some coefficient in this series, and there is some prefactor which is important, but in this talk it will not be much important. So I will not explain what is here, but there are kind of 2 parts in this. There is this prefactor, and then there is this kind of theta series part. So I will mostly talk about this part. For some easy manifolds like length spaces, you actually don't get any theta functions here. You only get a prefactor. But most of the time, you will see some theta functions or something more complicated. Yeah. If we now consider just 3 singular fibers, so we have a ciphered manifold with 3 singular fibers, then it is well known that this invariant ZB is expressed in terms of some false theta functions with some R, some residue class modulo 2M, and with some modulus M. And it's kind of funny, but people study this for a long time, and it's still not completely clear what are these numbers M and R1 up to Rn. If I write you a manifold, so I want you to tell me the R's and M. So basically, this is like an important question. We would like to express these numbers in terms of the cipher data rather than the matrix, which is huge. Yeah? So these integrals are huge, and we want a simple expression. So one way we can approach this is to consider these generating functions. So we take the character for each of these theta function, and we assign to it the generating function, which I defined over here. So we basically assigned to this expression. This also is actually interesting in this whole story of Z heads, because these invariants, they are coming from Chern-Simons theory. The important relation to the Chern-Simons partition function is that if you sum all of them, and then you look at the radial limits to the roots of unity, you actually recover the Witten-Reshetikhin-Turaev invariant on the level k when you have a root e to the 2 ik. So this is pretty, yeah.
Be a bit more clear about which things are theorems or beliefs or conjecture?
Okay. So it is a theorem that this is related to Chern-Simons theory.
Okay, for this plumbed manifold?
For these plumbed manifolds, yes. There is also a version for other manifolds, and I don't want to say anything about it. Okay? Yeah.
And this is a theorem that equals these sides.
This is the definition, and this is a theorem of Brinkmann and company. So they consider slightly different. Yeah. I think it is a theorem. Yeah.
How is it they prove such a theorem without telling you what it is?
Yeah, that's now I'm also thinking about it. So the thing is that they consider some slightly less involved functions, which don't have these funny shifts. Here you have these funny shifts. You sum over the lattice, but you add some. So I forgot to say very important thing. What is this label A? So this label A is an element of H of this H1, or you can also think about it as a spin C structure on the 3 manifold. So this element A gives us some shift in the summation. so they consider something slightly less, something slightly different, and they compute it and they get expression in terms of psi functions. So now I'm not sure if they actually really prove it for the ZAQ, but at least for something very similar. But yeah, it's a good question. And sorry that I was thinking about this question a lot, but now I forgot. So maybe I think it's like this, that from their proof it's clear that there are some R's and M, but they don't really compute them explicitly, or they don't have. So I mean, in principle, you can compute everything. This is just an integral, but like to find a nice formula, it's not that clear. Yeah. So so as I said, this gives us the Chern-Simons partition function, of which we think as a Q series. And so we can write the sum of these generating functions and call it FB, and then we can consider sum of all FBs over all spin C structures, and we get some generating function for SU2, the partition function. So if you exponentiate this variable, so if you consider e to the x over here instead of x, you will get so-called like function which defines the Borel plane. So you will get the Borel transform of these partition functions. So this is interesting for physicists and for the resurgence theory. Yeah. So as I said, I want to mainly talk about examples. So one interesting example, which has been studied in a paper of Kazuhiro Hikami, but when it came to the computation, so at that time there was no Z hat, so he didn't know these formulas, but he was still trying to express WRT in terms of some nice false theta functions, and this was the one of the 14 singularities of Arnold, which he struggled with because of a simple reason, and that's that the H1 is actually very big here. It's Z over 13Z, so the computations get very messy. But now we have more formulas, so we can deal with that. So this singularity is given by this equation, and the link is just this ciphered 3 manifold with the orbit numbers 3, 4, and 5. So as I said, H1 is Z over 13Z, which you can compute as the orbifold Euler characteristic, which is just sum of these 4 numbers times the product of these 3 orbit numbers. And if you consider the universal Abelian cover, then by this theorem of Neumann and Wall and others, this is originally theorem of Neumann, which was then generalized to many other cases. The universal Abelian cover is just a singularity which is given by x to the 3 plus y to the 4 plus z to the 5th, where these are the orbit invariants of this manifold. So this is a very nice singularity. It is this Brice-Korn type singularity. It's a hypersurface singularity because we have 3 singular fibers. If you would have 4, then there would be 2 equations. And there is a nice diagonal action of H of this cyclic group on this singularity. So it is, it's very tempting to try to think about this manifold, which has this H, and we have invariants labeled by H, right? We have invariants labeled by elements of H. It's very tempting to think about this universal Abelian cover and the action of H. So here are some Z hats of S12 computed in Mathematica. So I wrote only 2 of them because they are somewhat similar. There is one thing which is good to know, that there is actually some symmetry. So Z hat of 1 is the same as Z hat of 12, and Z hat of 2 is the same as Z hat of 11. So if we have like number and minus number modulo 13, they are the same. So there's effectively just 7 functions. So you can see that there is this quadratic growth, yeah. And you may ask, you may ask, what is the number M? So this is something which was not really clear, and then you can ask what are the numbers R1, R2, etc. So the number M is 780, which is 60 times 13. So it's clearly related to these numbers because we have 3, 4, 5. This gives us 60, and then we have 13 somewhere here in the Euler characteristic. So this is related. And you can see this somehow from the Q series, because if you look at these two numbers and you add them, you average them, you will get 780. And over here, if you average them, you will get 780. Yeah, and this works for all of them. So that's, I mean, that's a stupid way how to see them, but there is like, you can see the number there. So if you want some time to compute it, it's really gives you 780. Yeah, so these are the invariants. And so let's now look at the sum of them. So we have 13 of them, and yeah, so one reason why they are interesting is actually that you have these integral coefficients up to this 1/2, but you can kind of trade it for the fact that you have 2 of them for each number different than 0. So there is some hope that there could be some categorification of these series, or maybe there already is, at least in the physics literature. So if we sum them, we get such a series. And now you see that there is always this q to the 1/13, which was kind of hidden here, but it was actually here because there is this prefactor. And so if you look at this series, and then you can recognize the number 60 there, because if you look at 47 and 73, the average is 60. And it's really true that this is actually some combination of these series of these false theta functions, but now with modulus 60, not 780. Except that we need to consider the different variable, which is like q to the 1/13. So this is some kind of very nice cancellation which happens here, even though that we have many 780 theta functions, modulo 780. When we sum up them to the Chern-Simons partition functions, we actually see that there is these exponents only like care about modulo 60. Yeah? So if we compute the generating function, we actually get something very, very nice. So maybe it's surprising, maybe it's not. There were some formulas like this known for like Brice-Korn spheres, also in the work of Hikami. And I think it's not, in the end, it's not that surprising that you have something just, it must be something which depends on the cipher invariance. Yeah.
You computed a bunch of series by doing some integrals, you added them together, and you get this.
Yes. So this is the generating function. So for example, there will be theta functions which has the residue 3 times 4 times 3 plus 4 times 5, except that you need to subtract this 60 because over here there was this m minus r right over here. Yeah, so this is a nice way how kind of package all these. So if you now plug like e to the z instead of x, you get exactly the function which defines the Borel plane. So this should be something very fundamental for the free manifold. Yeah. So my expectation is that there is such a nice formula for all of them, because I mean I tried many examples. I didn't prove it. It should be easy to prove it. Once you have the formula, you just need to kind of compute these integrals. And this was done for Brice-Korn spheres, and then for some more general case, it was not done for S12. But you just follow the same steps, and you if you know what you want to get, you will get it. It's just about playing with this lattice. Okay, so So now I have some speculation about the geometry. So as I said, it's kind of natural to hope that these invariants of M can be expressed in terms of this universal Abelian cover and this natural action on H. And we know that if we get these three singular fibers, then the function which defines the universal Abelian cover is just x to the a1 plus y to the a2 plus z to the a3, where a1, a2, a3 are these orbit invariants. So that means that in our example, it's 3, 4, and 5. And if you look at the Poincaré series of this ring, so this is a graded ring because this is a weighted homogeneous polynomial. So you can assign weights to the monomials in the quotient ring, and you can compute the Poincaré series. And this is some standard computation which gives you 1 minus x to the a over 1 minus x to the a over a1 a to the a. Sorry, there should be 2 here and 3 here. This is a typo. So so a is the least common multiple of these three numbers. So if you look at this, these 3, 4, 5. Oh, sorry, I was kind of in a rush, and I think I wrote many stupid things. So instead of 3, 4, 5, there should be exactly this 60 over 3, which is 20, then 60 over 4, which is 15, and 60 over 5, which is 12. So this is wrong. There should be 20, 15, and 12. So in this case, in this very special case of three singular fibers, this series up to this thing with powers, which is actually very important, but at least in the case, there is a special case when the Euler characteristic is 1 over this number a up to sign, then it perfectly matches the inverse of the Poincaré series. So this is kind of cool, even though this may be very random thing, because, you know, as Nemeti said in the previous conference, everything about all the invariants of the quasi-homogeneous singularities are the same, whatever you do. So so this may be just a random thing, which we will also see. But also what is nice is that we can think this is just for the SU2, this is just for the whole thing, the sum, but we can write such functions for ZB, which add up to this function. And similarly, we can consider the H equivariant version of this Poincaré series. So there may be a relation which is also taking account of these groups. This talk is not really about three manifolds, but we were talking a lot about stringing spectra in our previous in my previous talks, for example. So the stringing spectrum is actually related to this Poincaré series by a theorem of Abelian. So you just need to multiply by some factor and do this cyto duality of polynomials, of invertible polynomials, and you will get the characteristic polynomial of the monodromy. So the monodromy of this universal Abelian cover is somehow hidden here. Yeah, so now there is another example which is, I think, quite interesting, and this is something which you may already notice from the previous example, and this is actually that this series seems not to really care about the numbers b in these numerators. It cares in the sense that there is somehow there is the Euler characteristic in it, because we have this 13 power here. Yeah, so we can also write the general formula which only takes into account this a1, a2, a3, and the Euler characteristic. So now if we consider these two manifolds, so one is -1, 1 over 7, 1 over 7, 4 over 7. And the other one is pretty similar, it's just 1 over 7, 2 over 7, and 3 over 7. So they are made so that the Euler characteristic is the same. And also the H1 is the same group. So they are pretty similar, but apparently they are not homeomorphic because of a theorem of Orlik, which says that these two manifolds, so if you have ciphered manifolds, most of them are so-called large ciphered manifolds. Basically 3 or more fibers up to some special three fiber, which is not this case. And the theorem says that then these manifolds are actually determined either by the fundamental group or more strongly by the cipher data. So these have different cipher data. So they are different as a cipher vibrations, but they are also non-homomorphic. It would be very, very boring if they are homomorphic, because what I'm going to say is that they have very similar these invariants. So if you look at the Z SU2 of the first one, we see this series with prefactor Q to the 5/7. And if you look at the second manifold, we see the same series, strangely enough, with the Q to the -4/7. So I think this is something surprising for the people who study these Z-hat invariants. Even though, I mean, I'm not an expert in this. I'm very new in this, so for me it's like, okay, so two nodes have the same Jones polynomial, or I don't know. So it's like you know, so there are some manifolds which are so similar that it happens that they have the same Borel plane. So this can be written in terms of theta functions as psi and psi, psi6, psi4 modulo 7, because you can see that the average of 3 and 11 is 7. If you look at
what is this constant discussion you have about the average of two numbers?
Yeah, that's my way how I recognize the functions. You know, I mean, the functions are kind of simple, right? This is just like Q to the n squared over 4 basically, and there is some residue class there. So you are summing over residue class something which grows quadratically. The only confusing thing is that this is a sum of few theta functions. So you can get confused which terms you know is in which theta function. It's kind of, you need to split it into linear combinations of theta functions. So one theta function is starting this -1 Q to the 3 Q to the 11, and the other one starts like this. And if you make this, so this is just like some property of a quadratic function that if you you know, average some terms, you will get something like the modulus. Yeah. So here, if you subtract 5/7 from these terms, then you can see that this number plus this number, which with both subtracted 5/7, will give you 14 again. So there is one theta function over here, and there is second theta function over here. Yeah, but of course, this is actually a sum of 49 Z-hats. So there are many of them because this is a very big group. Most of them are actually 0, which is also kind of interesting. But there are 7 or 8 non-zero functions here, and they are also written as a linear combinations of theta functions. So actually, you have like a lot of theta functions, which may be kind of hard to recognize, but if you sum them all up, you will get just 2, which is nice. So if you now look at so does it answer your question? Yeah.
Sure.
Yeah. So if you now take the generating functions, then you see that if you take 3 times x minus x to the x minus 1 plus this thing, you will get this, which is very nice because here we have that the invariants are 7, 7, 7. So we have 7/7 is 1. So we had just this 3 times over the x to the 7 minus x to the -7. 7 is the least common multiple. So this is basically the reason why they are the same, because the manifolds are different, and it is manifested in the fact that they have different prefactors, which you can write down explicitly. But this kind of Borel plane information, theta functions information is actually the same because it's given by this simple formula. Okay. So I'm coming to the last example. So now I will consider singularity x4 plus y to the 5th plus z to the 6th. So this singularity now is more complicated because if you look at the link has 4 singular fibers. It's still very simple singularity, but at least it's not it's something more than 3 singular fibers. So you have this nice plumbing graph, and you can write you can compute first of the easy invariants like the Euler characteristic and the H group, the H1, and then you can try to write down the Z hats. And now this gets really messy because you need to compute these integrals for such a big matrix, and there is not an expression in terms of these false theta functions. What you need to do is consider combinations of false theta functions of this form, and then the theta functions which have a prefactor n here. So they have linear prefactor in front of this quadratic exponential function. So in terms of number theory, this is like quantum modular form of this like height 1/2, and if you add n, you have like 3/2. So this is a mix of two kind of functions, which makes it much more messy. But actually, I looked at this example, which was this was studied in the paper 3D modularity of Cheng, Gukov, Ferrari, and others. Sorry, I cannot remember. So even though that this is like a combination of weight 1/2 and 3/2, and in general you expect that there will be like 5/2, 7/2 if you add more and more singular fibers. So this is kind of mysterious. I think it has quite a simple explanation in terms of these generating functions, because if you compute the generating function, so you need to do a careful analysis of these Z hats and see what kind of false theta functions of weight 1/2 and weight 3/2 are there. But if you do it, then you actually recover this formula. So again, 30 is the modulus of the theta functions, and here 15, 10, and 6 are again 30/2, 30/3, 30/5, and you see this is twice there because we have two singular fibers for 2/5. But it's not completely like the previous thing, because there is this funny additional term. So it was my like naive hope that we get just something which is pretty much related to the Poincaré series. But we can write it in this way. So we can write it as these 3 terms, or actually 4 terms. And then this is just the derivative of this function 1/x to the 30 minus x to the minus 30. I have no idea why, but it seems, I mean, again, it seems like very promising that this formula can be generalized to at least all the star-shaped singularities. And what is actually interesting about this, that so it kind of looks like an inverse of some Poincaré series, even though the Poincaré series for the universal couple is just this. So it's pretty similar, but there is this term over here, or this derivative, if you like. So it's something different. But if you invert these series, you actually also get only positive, or actually only negative coefficients because of this negative sign. But so it looks like that the inverse is a Poincaré series of something. So this, I think, would be very interesting to think about. Yeah. So this is the generating function for this example. Yeah, and that's basically all I wanted to say up to the things which I forgot. So the conclusion is that there are some easy and kind of unexpected explicit formulas for these generating functions. And so the obvious question is, what does it mean conceptually? So why are there such an easy formulas? What they mean for the Z-invariants? What they mean for 3D topology? Then we have the manifolds with the same Borel plane, with the same generating function. So apparently this is surprising. So what does it mean for the resurgence analysis and for Chern-Simons theory? Then the question which I'm personally very interested in is how these generating functions are related to the invariance from singularity theory. So in the last week, there were talks of András Nemeti, where he talked about his lattice homology and about all these relations of the links and the singularities. So this is pretty much my original motivation, how I even started thinking about these Z-heads, because I could somehow see the numbers of the steam ring spectrum in these expansions of in these Qs, yeah, for the Poincaré sphere. So and I mean, it's not the same, but there is a kind of, you know, it would be kind of hard to guess this formula if I wouldn't try to compare it to this one. I tried to compare it to this one, and I got just this last factor. So at least like a motivation for this work, it's useful. And so the last thing is what about, so of course now we want formula for ZB, because I only presented formulas for like SU2. So this should be some more refined, because it should depend on this element of H or the spin-C structure. But basically it should be also such a simply, I mean, it must be such a simply function, right? Such that if we sum up these 49 functions, for example, 49 functions over here, we will get this nice function over here. Yeah, so they may, and that's like another question is if, so in this case, they actually look the same. I mean, maybe up to this, some like ordering, but the question is if I can have like different Z-heads and the same Chern-Simons function. That's also another interesting question. So yeah, so I think this is like this is basically, I hope everything like planned for a very for very soon future, like that, you know. So the last question is, can we say something about more complicated manifolds? So if we have not a ciphered manifold, if we don't have a quasi-homogeneous singularity, but some kind of more graph with more vertices of valency 3, can we write such an easy formula for them? Because we can compute the Z-head invariance for any plumbed manifold on the computer, so we can try to search for such formulas or try to prove them. Yeah, here are some references, but there are many references missing. Also, again, because of the time. Yeah. So are there any questions? Yeah, I think this is basically all I wanted to say.
Are there any questions? I have a question. Is there any interpretation of these formulas using some kind of Griffin degree Monroe with Todd classes or anything?
Oh, you mean these Z-heads?
Yeah. Or the derivation, is there any?
No, I don't think so. I mean, at least in the original derivation, I don't think there is something like that. But
this X15, all these terms that they.
You mean these terms?
Yeah, that show up. No, the ones X15 minus X to the negative.
Yeah. So
they kind of smell like some kind of Todd class if I set X to be e to the something.
So I forgot to say something very important. That's like that I'm really new in this. So when I see this, I don't have anything like this that I would say, oh, this looks like something. So if you have such like feelings, that I'm really curious about them. Yeah.
Steam ring spectrum related.
Yeah, that's why.
Yeah, steam ring spectrum is related to the Poincaré series. Yeah, also to Gukov.
That's why. That's where probably.
Yeah.
Maybe this was in the beginning and I missed it, but you went through two examples, and then you said that okay, now the formula is generalized when you star whatever.
4 fibers or
Did you at some point say what the general statement is?
No, I didn't. That was kind of intentional, but it's like so I think the statement. So this is the statement if in the simple case when you have like, I mean, you need to invert this, and then if you have the case when the Euler characteristic E is minus 1 over A, the least common multiple, then you have just this inverted. And if it's not, then you need to, so it's gonna be something like 1 over E times A1, 1 over E times A2, 1 over E times A3, and 1 over, yeah, something like that. So this was basically because of the lack of time, but I think it's pretty straightforward to write it.
Prove this statement, or you think?
No, I haven't proved this statement. This is a conjecture, yeah. But conjecture with, I hope, very obvious proof, because you just need to manipulate this. Yeah. So it's kind of, yeah, I should first prove this, but there was no time to. This is very recent. These are very recent examples. So of course, this formula may be wrong. Sorry, this formula may be wrong. But I think the variety of the examples is now kind of like sufficient to strongly believe that there is nothing nothing more there.
But in this example, you prove.
Yeah, in these examples, yes.
And then you have some explicit conjecture about what is true in general.
Yes. For the 3 singular fibers, these 4 singular fiber I computed this weekend. So I mentioned this thing about this derivative, but I think it's too soon to say like whatever it is. Yeah, but yeah, it's basically just a question of looking at examples and then computing this huge sum and be aware what I want to get. So yeah. So I think the good way to do it would be to first find the explicit formula for the ZAs, because it's kind of harder to say something about the sum of all of them. Yeah.
Let's think, Joseph, again.